Welcome to this week's CSP seminar. It's my real pleasure to introduce today's speaker, Professor David Hong of the University of Delaware. For those of you who don't know, and probably most of you do know, David graduated with his doctoral degree from here at Michigan in 2019. And then he was an NSF postdoctoral fellow through the University of Pennsylvania for a few years, like through most of COVID and whatever, I think. And then he joined the University of Delaware in 2023. And with that, I'm going to turn it over to you for your presentation. We look forward to hearing it. Sorry,
Yep.
So thank you.
All right. Thanks so much. And thanks, Jeff, for the invitation. It's really fun to be able to come back home in a sense and see Ann Arbor and to be able to give a CSP seminar. I sat in many of these over the course of when I was a student, although I guess they were on the first floor back then. So, okay. So the, let's see. Yeah, so the talk today is going to be about some adventures in PCA for heterogeneous data. It's going to be a talk kind of in three parts. The first is going to be some motivation. The second one, we're going to talk about optimal weights. And the third, we're going to talk about rank estimation. It's sort of an adventure, I guess I began during PhD studies here with Jeff and Laura, actually prompted by, I guess, the first problem that Jeff and Laura gave me to think about. But yeah, it's been a lot of fun. And actually, as you'll see, there's still actually lots to do. So without further ado, I'm going to jump right in. So, okay, so I think the people on the Zoom are seeing my screen. So let me make this a little smaller. Sorry, one second. This is designed for the projector, so I might have to zoom out a little bit here. Let's see. Oh, it's not too, let's see, it's not too. Oh, okay, but you can see the rest? Oh, great, okay. So, all right, so the kind of at a high level, so I'm a new professor at University of Delaware, and kind of at a high level, what I'm trying to work on in my lab is on how to do low rank estimation in the context of heterogeneous big data. And why? Well, because heterogeneous big data really is everywhere in modern analysis, data analysis. Here I'm showing kind of three representative examples that kind of show that heterogeneity really arises everywhere from the microscopic to the telescopic, right? So to the cosmic. So on the microscopic end there, that's cryo-EM, not expectation maximization, that's electron microscopy. Though people do EM algorithms for EM, so that's kind of fun. In that context, they're imaging these small molecules, but they get the same molecule viewed from many different orientations. Okay, so you get numerous snapshots, but with heterogeneous views. Typically, you don't know which view you're getting at any particular time. In the middle there is air quality data. So you could have maybe a bunch of air quality sensors distributed, and you might have some really expensive ones maintained by the EPA. And then you might have some sort of consumer grade household ones that people plugged into their by their home. My wife and I lived in San Jose for a while, and definitely in the Bay Area, there's a lot of concern about air quality. And then, so the telescopic end here is an example of quasar spectroscopy. So this is imaging of distant quasars, and there we've got often heterogeneity in the noise. Cool. So there's lots of other settings. Many of you, I think, probably can think of some in medical imaging. There's actually a lot of this stuff also comes in genomics. And more generally, omics data. And then there's also places in radar where this comes up. So the list goes on and on. All right, and now why? So that's why heterogeneous big data, but why low rank estimation? Well, a lot of data sets naturally take the form of matrices and tensors. And one thing I think a lot about is, well, you know, especially if we put on our electrical engineering hat, right? We know that on the computer, this might all be just stored as a long list of numbers. So really, when we say it's a matrix or a tensor, this is a conceptual decision we're making to view it as a matrix or tensor. And why are we doing that? Typically, it's because we think there's some kind of shared structure, right? There's some meaning to the rows, some meaning to the columns, or in general, for tensors, you run out of names, you start calling those mode 1, 2, and 3, right? And there's some reason why we're interpreting it that way. And actually, sometimes there's a bit of an art of whether you interpret it as a tensor or if you flatten it out or things like that, okay? So in other words, the very fact that we formed our data into a matrix or a tensor conveys that we believe there's some kind of structure there to be found. And so finding that structure is a really fundamental task. And that's why it comes up all over the place. All right. And so a workhorse method for finding structure in data, and matrix and tensor data are these low rank matrix and tensor estimation techniques. It's sort of fitting maybe that the same kind of ideas have been reinvented many, many times, right? If you think about SVD, PCA, a lot of these things are very related. Likewise, in the tensor world, actually, what I'm showing here is the canonical polyadic decomposition, or you might have also heard it called the Kennedy-Comp parafact decomposition. It's because it's been reinvented multiple times, and conveniently, CP can be used to capture all of them. So, all right. And so the question here at a high level, again, is how should we account for heterogeneity when we're doing this sort of stuff, right? And now, one thing I forgot to mention is that it's a workhorse method and that it's a really fundamental and foundational technique, but it's also part of a lot of data processing pipelines. So for example, in GWAS, when they're doing these genome-wide association studies, sometimes what they'll do is they'll look at principal components of that GWAS data, of the SNP data, and some of those principal components capture some of the ancestry information of like who's related to whom, and they'll try to remove that so that they can find the associations that aren't just due to like being from the same population. Okay, so okay. So within, kind of within this broad umbrella, a lot of the stuff I'm working on right now kind of falls in a few buckets. So one sort of research thrust I'm working a lot on is dealing with heterogeneity in the noise. So here we've got a data matrix which has a low rank signal plus a heterogeneous noise matrix. I don't know if there's any stats folks in the Zoom, so apologies. The samples here are columns, but so the noise matrix here, you can see there's different sigmas across the columns, so different samples have different amounts of noise. On the right here is sort of an illustrative example. What I'm showing here is a bunch of quasar spectra. So each column here is one of those spectra. And what you can see is the first 3,000 of those are much cleaner than the last 2,000 or so of them, right? Those are a lot more noisy. Okay, and
I don't know if you want to turn on your camera.
Let's see. With where the iPad is, I guess they'll get a view of my nose, but let's see, maybe.
Okay. Oh, never mind.
Yeah. Fair enough. Yeah. A second example here is heterogeneity in the signals. And so here, rather than the, I guess I could sign in quickly or no. All right. So here, the noise you can suppose is homogeneous for now, but in the signal matrix, different columns there have a different factor matrix F. In other words, it could have different low rank structure or low dimensional structure. And so there's a bunch of kind of examples of this sort of structure. For example, if those Fs, if each column there is corresponding to time, progression over time, then you could have those Fs maybe slowly varying from column to column. And this would be the subspace tracking problem where there's some subspace that's evolving and you're trying to track it. What I'm showing on the right here is a place where we're trying to apply some of these techniques. In particular, we're looking at hyperspectral imaging of artwork. So I've got a collaborator in conservation science, and they do they look at artworks and they image it across, let's say, 200 or so bands. And what they want to be able to do is figure out, for example, what kind of pigments were used at every pixel. And this is important for the conservation scientists to do all sorts of things. I think sometimes they even use it to do like attribution. They might say like, oh, this material couldn't have used that, blank time period. Oh. Yeah. Oh, okay. Okay. And so here the idea is that different pixels have come from a different pigment, and there's maybe an associated low dimensional subspace for each pigment. And so the task here is to try to divide up the pixels by subspace. Okay. So that's heterogeneity in the signals. And then kind of the last thrust of work right now in my group is looking at tensor decompositions and trying to generalize them. So on the left there, you could suppose, for example, that your data tensor arises from some distribution, which is parameterized by some low rank signal tensor. Okay, so for example, that's Gaussian, then you could think of that as a low rank signal plus Gaussian noise. But this eventually boils down to some kind of minimization problem over low rank tensors. with respect to some general loss. And so there's a lot of work to be done on developing both general purpose algorithms that can handle all sorts of losses, but also specialized algorithms for particular losses that are really important, where we can maybe exploit the structure to accelerate things. So yeah, I think well, we'll see if I can pull it off. But one of my ambitions maybe is that, in MATLAB, people joke, or in Julia, whatever your language of preference, that the backslash has a bunch of algorithms underneath it, right, where it'll dispatch appropriately, and it'd be really cool, I think, to have something, probably not that good, but in that direction. So, all right. So today we're going to be focusing mostly on this first thrust, but I just kind of wanted to couch it within the context of why I think this is all really important. And so this example here again is quasar spectra from, and this is from the Sloan Digital Sky Survey, which is a giant astronomical survey. And here we're looking at, on the left, that same data matrix. On the right, we see, you can see 3 of those spectra I pulled out, just exemplar ones, where the green one there you can see is quite clean. The blue one is a much noisier one, but you can see they all have basically the same shape. And that's why we might believe that there's some common low dimensional structure to find. All right, but there's heterogeneity, so commonality in the signal, but heterogeneity in the noise. And the question is how to perform PCA for data like this. Okay, so this is a really kind of in a growing area, so it's been really exciting to be in the thick of this. You'll recognize a few of the names up there. But there's a bunch of work on dealing with heterogeneous noise across samples, which is what I'm going to talk about today, primarily. There's also work on dealing with heterogeneous signal strength across samples, which if you think about it is kind of dual to heterogeneity and noise, because if you renormalize, you could make the signals uniform and you would end up with heterogeneity in the noise strength. There's also work on dealing with heterogeneity that's across both samples and features, or maybe just across features. And then finally, there's a lot of work on rank estimation. So yeah, so there's been definitely a kind of exciting thing to see. And actually, there's even some more that I just couldn't fit because of space. So this is kind of I think it's an exciting area to be working in. And today we're going to be focusing mainly on these 2 papers. So part 2 will be the first one and part 3 will be the second one. All right, so without further ado, part 2, we're going to talk about here optimally weighted PCA. Okay, so I hope you're motivated to think about these sort of problems with heterogeneous data. One of the things I also want to convince you of today is that PCA is truly a textbook method, right? It's something we teach at the undergraduate level, but hope to convince you that also there are still things that we don't know about it. And it's so ubiquitous that it's important that we figure out these problems, these challenges in modern settings. So here's the model we're going to consider for this part. We're going to have a data set or data matrix Y, which is D by N. And we're going to think of it as being made of some blocks of samples. So here there's 2, Y1 and Y2. All right. And, sort of geometrically here, I'm thinking of each sample here, or sorry, each column of this matrix is some data point in a D-dimensional space. And why are we doing PCA? Well, maybe because we think that those data points lie maybe roughly along some kind of low dimensional subspace. In this case, I'm drawing a line. And now if you look, those blue dots, those blue points are coming from that first block. They've got a much smaller noise variance, and so they're much closer to the line. The red points there have a larger noise variance, and so they're further spread away from the line. Okay. All right, in this case, the red dots have a noise variance that's 19 times as large. Okay, so this can all be formalized. We write it sort of mathematically here. We have that each block there is going to be some factor matrix F times coefficient Z plus noise. Okay. Now, notably here, these the columns of the factor matrix are scaled. Essentially, you should think of them as eigenvectors. Okay, the U1 through UK. Those give us the basis for the low dimensional subspace. And then now we have these lambdas, which are signal variances, i.e. signal strengths. And then we have noise variances, VL. So each block has its own associated noise variance. So V1 and V2 in this case. Okay. And the goal is, given that data, try to estimate the low dimensional subspace. Try to estimate the basis vectors. All good? All right. So A natural approach for this is, well, what do we do in the homogeneous case? Well, we've got homogeneous noise. We have data points that look kind of like in the top left there. And the standard thing to do is to do PCA. What do? We form the sample covariance matrix there, and then take the ith leading eigenvector. Right? We take the leading eigenvectors of the sample covariance matrix. That's the PCA estimate, you could think, of those basis vectors. Okay. But now we've got heterogeneity and noise. And so a natural thing to do is to modify this to instead consider a weighted sample covariance matrix, where now every sample, or you can think every block, is going to be weighted by some scalar, right? And so that's going to allow us to give noisier samples or noisier blocks of samples less weight, right? I like to think about this as like, we do this all the time every day, right? You maybe got a couple friends who give you their opinion. You know, one person is maybe a little less reliable, right, in their opinion. So you might give them a little less weight when you're putting it all together, right? And so it's just the exact same thing here, okay? All right, so this is a very natural idea, right? But of course, now the question is, how do we choose these weights, okay? And so, oops, before I go to that. So actually, yeah, I think we can do it. Here's where I'd like to maybe get some interactivity. So some of you maybe know the results of this paper. So for those of you, I'd request that you don't speak up, but I'd like to hear some thoughts on, you know, what are some proposals you all might have for how might you choose the weights? So here, again, the blue points here have a noise variance of 0.1. The red points have a variance of 1.9, so 19 times the noise variance. So the question is, how much weight would you give to those two blocks of data? Okay, yeah. So what I'm hearing is W1 would be 1 over V1, and W2 would be 1 over V2. Yeah, very good. So these are inverse noise variance weights. Very natural, I agree. I think it's actually what Jeff, Laura, and I would have also thought a priori. And one thing that they do is that they actually amount to widening out the noise and making it homogeneous. Yeah, very good. Are there any other ideas? So likely a bad idea would be to set them both equal to 1. So that would be unweighted PCA. Right, so that would be sort of not accounting for the heterogeneity, which, you know, if it's not that heterogeneous, maybe that's reasonable, right? What if instead of the second noise variance being 1.9, it was like 1.9 billion? What might you guys think of doing in that case? Say again? Yeah, just throw it away, right? So we might just say, oh, this data is garbage, let's just throw it out, right? And so that can actually be thought of as a weighted PCA, where W1 is 1 and W2 is 0. Right? So if we choose binary weights, that's a way we can throw away data and keep some data. Make sense? All right. Now, there could be computational benefits to doing that, right? Maybe I've got less data. I don't have to compute for as long. Today, we're going to be mostly concerned with the statistical performance. All right. Okay, so are there any other ideas? Okay, these are the main ones that we came up with. I also always like to ask to see if folks have other ideas. No one so far has guessed the optimal form. So, but I'm hoping one day. I've asked a lot of audiences. These are the existing choices that you'll often find. So there's unweighted PCA, don't account for it. Throw away the noisier data and whitening. All right, very good. But now if we take a step back, in a sense, what are the weights I wish I knew to use? Okay. So what weights do I wish I knew to use? Well, you can think about it this way. So notice the estimate UI hat is a function of the data, but it's also a function of the weights, right? And so I wish I knew what choice of weights made that estimate as good as possible, right? So how could we think about that? Well, we could measure here the inner product squared between, oh, I'm sorry. Maybe it's my adapter. Oh, okay. So we can look at the inner product squared between the ground truth UI, so that's the true basis vector UI, with the estimate UI hat, right? And we want that to be as close as possible to 1, right? If it's exactly 1, it means we nailed it. If it's 0, it means we totally lost it, right? And so we can think about choosing the weights that make that as large as possible. right? In other words, we want to choose the weights that maximize this performance. Does that make sense? So these are the weights I wish I knew to use. All right. Now it's going to be a function of the data. Why? Because for different instantiation of data, there might be some different way of twiddling with those weights, like turning those knobs to get the estimate as close as possible to the ground truth. All right. Okay. Now notice, in practice, I can't really do this because if I knew UI already, well, I wouldn't be doing any of this in the first place, right? But in principle, these are the weights I wish I knew to use. Okay. So now here's sort of an illustrative example where what we've done here is generated data, which is, it's got two blocks, noise variance is 1 and 3, all right? And since we've generated the data here, we know the ground truth that we use to generate it, and we can actually play with that knob and find the optimal choice of the weights. Yes. Now, one thing to keep in mind is, well, if I double all the weights, the eigenvectors don't change. So it's all that matters really is the relative weighting. How much more weight do you give to the, or how much less weight, sorry, do you give to the noisier block? So that's what we're showing along the horizontal axis here is the relative weight given to the second block divided by the first block. Okay, where again, those weights were chosen by actually optimizing, choosing the best choice of weighting. Okay, so these are the weights I wish I knew to use. And what do we find? Well, in the first case on the left here, we're looking at, we're in 100 dimensions and we're looking at the first block having 400 samples, the second block having 800. And if you look at the, what I've done here is, I forgot to say, we've done a bunch of instantiations of data. And for each instantiation of data, we get a different choice of optimal weights. And so we can do this a bunch of times, make a histogram. Okay. What do we see? The optimal weighting, first of all, it's typically not near 1/3, which would be the inverse noise variance weighting, right? Here, the second block is 3 times as noisy. Inverse noise variance weighting would give it 1/3 the weight. Okay. Nor is it at 0, which would be throwing away the noisier block. It's somewhere in between. Okay. It's almost always somewhere in between. Right? And now, interestingly, also, as we go to higher dimensions, so take everything and just make the data 10 times bigger in all dimensions. What do we see? On top of that, that distribution of optimal weights is concentrating around a single point. Cool. All right, so the takeaway here is that none of the existing choices are optimal, and there's something else that's optimal. And on top of that, as the data matrix gets large, it seems to become less and less random. All right. Questions so far? Okay, so the natural question is, what is that line, and is there a way to predict that without knowing the ground truth? Make sense? Okay, can anyone eyeball like what you guys think maybe the optimal might be here, or the limit? Yeah, it's like about 1/6, right? So it might be tempting from here to say, oh, maybe we should do inverse noise variance divide by 2, right? Just forgot the divide by 2 rule. That's what you do on exams, right? I was off by a factor 2, so I just divide by 2. But you know, so that might be a conjecture, but we don't know if that would hold in general, right? And so here is the main result, which is a theorem actually giving a formula for that optimal, for the limit of the optimal weights. Okay, so in particular here, what this theorem says is that as the data grows in size, so when the data gets larger and larger and larger, or you can think about it as long as the data is sufficiently large, then those optimal weights, okay? So remember, these are the weights I wish I knew to use, which are random, depend on the data. They converge actually to this choice of weighting. Okay. Now there's an except when kind of case. This is the case where actually the signal is buried in the noise and no choice of weighting is going to let you get it. Okay. So as long as you can get the weights, or sorry, as long as you can recover the signal with a weighted PCA, these are the weights that accomplish it. All right. And if we look at the form of this, actually it's an inverse noise variance weighting, but there's a second term here multiplied, which depends on the SNR. And you kind of squint at it, you might be able to see that when the SNR is very high, then this V1 over lambda I through VL over lambda I will be essentially 0, let's say, okay? And so this thing becomes like inverse noise variance weighting in a high SNR regime, but in a low SNR regime, this becomes something like the square of inverse noise variance weighting. So inverse square inverse noise variance weighting, Okay. Yeah. Oh, lambda I, that is the signal variance for the ith component. Yes. So it's a signal strength. So actually, an interesting thing to note here is that these optimal weights are different for the different components. So for those stronger components.
That should be lambda 1 and lambda L, not lambda I, then, right? We go.
Oh, no. So the variances here are V1 through VL of the I signal component. Yeah.
Sorry, I forgot that part. Okay,
Mhm.
Yeah, okay.
Yes.
So you need different weighting.
Yes. Yeah. So yeah. So this was actually quite surprising. The proof, for those of you who are curious, I can show you later. Actually, this only pops out at the very end. Actually, in my thesis proposal, I wrote a conjecture. I don't know if you remember this, Jeff. I conjectured that it would be the solution of some system equation. So I had no idea that something so simple would come out. So this was really shocking. Actually, it makes it feel like there must be a simpler proof, but I've not found it yet. I don't know. So if anyone finds it, let me know. Okay, so oh, I will mention one thing which is not on the slides, but actually there's been some other work from folks in information theory where they've shown actually that this choice of weighting is information, like, so let me think about how to say this. One could ask, well, do I need to do a weighted PCA at all? What if I do a different algorithm? And they were able to show, at least in the rank 1 case, that this is information theoretically optimal as well, which is interesting. So my memory is I don't think they've established it for rank greater than 1 yet. Okay, so all right, let's revisit that illustration. And if we drop that asymptotic optimal on, there it is right at 1/6. And so what we can observe here, right, is that the asymptotic optimal weights are generally actually closer to what those optimal weights are. Remember, again, on the left, actually, the optimal weights are random, right? So for a particular draw of data, the actual optimal weights might have been, I don't know, close to 1/8, right? But in general, the asymptotic optimal weights kind of centered in the right place. And then secondly, as the data grows larger, those optimal weights are concentrating around that asymptotic optimal. And so if you use the asymptotic optimal, we're actually pretty close to the optimal weights. Let's see. Yeah, I don't know if I don't know if I have it in my head. Yeah, it might be on the earlier slide. 1.
Oh, 1.
Yeah. Yeah, I think when we were writing this paper, I played around a lot with numbers to try to get nice, nice even. Yeah. Yeah.
Yeah, although this is open bound, right? In practice, you don't know like the noise variance and also signal variance, right? How do you choose it?
Yeah. So that's a good question. So I don't have it in the slides here, but in the paper, we do talk a bit about estimating the noise and signal variances. In a sense, it's not a focus of this paper because how to estimate the noise variance, for example, can be quite also, that can be sort of application dependent, right? Because in certain applications, let's say in some applications, you have calibration data, for example. But we do in the paper talk about like a general kind of estimation of the noise variance. You can use the norm and sort of in the limit, the signal energy washes away and you're left with basically just the noise. And then for the signal variance estimate, you can use the eigenvalues of the sample covariance matrix. But you have to do some shrinkage to account for a positive bias that occurs due to the noise. But one thing I should say is actually I was hoping to. There's something I'm working on right now that is a way of doing optimal weighting to better estimate those signal variances. But I didn't make enough progress to be able to include it in these slides in time. So, but if you want, I can show you on my laptop later. Yeah. So we have some discussion in the paper though about this, but the punchline I'll say for now is that yeah, like first that there are applications, right, where you do know the noise variance and the signal variance, or you have a way of estimating them. More common, you would have an estimate for the noise variance than the signal, I think. And so it's good news that the signal in some sense variance is easier to estimate. And then secondly, even when you don't know it, you can estimate it. And interesting result is it's not hard to show that. Oh, I'm sorry, guys. It's not hard to show that if as long as your estimates for those variances are asymptotically consistent, as long as they converge to the correct answer, that if you plug those into the formula for the optimal weights, those estimated optimal weights remain asymptotically optimal. So everything sort of goes through. And sort of the mathematical challenge there maybe is that you just need to have, oh no, maybe for that part we're good. There's parts of this where basically you need to have uniform convergence. Yeah, and so that's the hard part, is to establish that. Okay, great. It's a wonderful question though. Okay, so now if we look at comparing how well this performs against other choices of weighting, the existing choices of weights, what we're looking at here are these two blocks of data, Y1 and Y2. And what we're going to do now is have the first block of data, Y1, which has got, let's see, 1,000 samples there. We're going to hold the noise variance at 1. And as we go from left to right, we're going to increase, going to crank up the noise variance for the second block of data. Okay, so as we go from left to right, second block of data is getting noisier and noisier. Okay. So if we do just unweighted PCA on this, what happens? Well, as that second block of data gets very noisy, the performance drops off. Oh, I'm sorry. On the left axis here, we're looking at the vertical axis, we're looking at the inner product squared between the estimate and the true basis. So how well do we recover the ground truth? Okay. And this actually jives with, some of you may know that PCA is not robust to outliers, right? And once the noise variance is large, it's sort of an outlier kind of phenomenon. Okay. Now, if you do inverse noise variance weighting, actually helps. And so we're not as effective, but interestingly, once the noise gets large enough, we still have the performance essentially going to 0. Okay. But now, one thing to keep in mind is if we had just thrown away that second block of data and only used the first block of data, well, that would be our performance there, right? And it doesn't change because, well, even though the second block of data is getting noisier, who cares? We threw it away, right? All right. And if we only use the second block, well, that's how the performance looks for that. An interesting thing to note is, why is the performance of that initially higher than only using the cleaner block? It's because that block is so much bigger. Notice it's got 10,000 samples, right? So when the noise is comparable, right, having that many more samples helps, right? But eventually gets so noisy that actually you're doing worse. Cool. All right. So we're left in a situation here where what we've got to do is we've got to debate for, regardless of which choice of weighting we use, we've got to debate at some point, maybe we throw away some data because we're actually going to do better by just throwing away the noisier data. But now if we add the optimal weighting on top here, you can see it appropriately combines the two throughout the whole regime, right? And so we don't have to throw away any data. We're always optimally incorporating the full data, okay? And so optimal weights here really make the best use of all the available data, okay? Now there's something to be said, once you're way out over here, right? And maybe the benefit of doing asymptotic optimal weighting over just throwing away the noisier data might be marginal, right? And so at that point, for computational reasons, you might do that, right? But that's a sort of different thing, right? A different trade-off than having to say, well, actually the performance is going to be worse. And this is kind of what we want for data analysis techniques, right? Is I feed it more data and it should continue to get better, right? All right. So I wanted to give you guys a quick piece of like a flavor of what the proof looks like. So a large part of the challenge here is that what we want is we've got here's the performance. And as I defined it, what we think about doing is optimizing with respect to the weights. And so that gave us the optimal weights. And then now we think about taking the limit of those weights to get the limit of the optimal weights. So we optimize, then take a limit. But that's really hard to do, actually, to do this optimization problem. You have to optimize like through an SVD, and this is a little hard to analyze. So instead, what we do actually is we take a limit first, and we get this asymptotic performance, which is a function of the weights. Then we optimize that. Unfortunately, that's also ends up not being that straightforward, but it has some really interesting structure, delicate structure that we can take advantage of. And we end up being able to optimize it to get these optimal weights. All right, so now you have this diagram that you can go this way or this way. And then you have to basically argue that this so-called diagram commutes. In other words, that those two paths lead to the same thing. So there's a bunch of ingredients involved in this. So there's some variational analysis and arguing that this diagram commutes In other words, that the limit of the optimum is the same as the optimum of the optimizer of the limit. Likewise, there's also some random matrix theory that's used here for computing these limits, some matrix perturbation theory, and then finally for optimizing this, we have to really carefully exploit a sort of interesting system of equations. So yeah, someone can find a simpler proof. I would love to hear it. Yeah. Okay, so just to finish this part, here's that quasar data we saw before. And here's some of our preliminary results. We've looked at unweighted versus inverse variance weighted and optimally weighted. And on the bottom here, I'm showing the recovery of a ground truth where, well, we don't really have ground truth here, but I've computed a sort of ground truth by looking at some of the clean samples as a proxy. And it seems to be more robust to adding in noisy samples. You can think that we've sort of taken clean data, removed some of the clean data, put in noisier data, and asked how much did things get messed up? And so it seems to be more robust. And so this is something I've been talking with some colleagues in astronomy to see maybe there's some promise here. Okay. Actually, we have a repo for this on weighted, a Julia package for this. And actually, I just got a issue from a colleague in astronomy posted an issue asking about some of this stuff. So, but they want more general versions of this. So, okay, so in this part, what do we see? We saw asymptotic optimally weighted PCA, some illustrations, roadmap of the proof, and illustration on real data. You can look at the paper. There's a lot more details there. We've got a lot more illustrations and comparisons, and as Peng brought up about how to handle unknown signal and noise variances. Okay. Any questions here? And so the takeaway here is, that when we're doing weighting, right? In some sense, I think actually one theme I wanted to highlight is I think there's some of this work I think is a nice illustration of how theory can help guide practice, right? Because the sort of natural choice of the weighting turns out to not be optimal. And it turns out that there's something else we ought to be doing. Okay. So now this next part is there's gonna be a similar thing that's gonna appear in this next part. Here we're looking at rank estimation. This is joint with you and Edgar. And so when you're doing PCA, one of the first questions you often hit is how many components should we actually keep? And so the problem is, right, we're going to imagine that we're given a low rank signal plus noise, given this data matrix. Here's a scree plot. And the question is, can we estimate from this data matrix that that signal was rank 1? Okay. Now, in that homogeneous case, you might have seen, for those of you who think about like elbow methods and stuff like that, you might see there, that looks kind of like the scree. And then here's the single guy that pops out. And so the challenge for today is going to be dealing with data with heterogeneous noise, where it's a little bit harder maybe to see that same scree structure here. You can kind of see it, but it's a little bit harder. Okay. All right. And so rank selection is very important, especially in the context where PCA is embedded in a larger pipeline. Why? Because if you select too many components, you're incorporating noise into downstream processes or analyses. And if you have too few, if you've selected something too small, then you've actually lost some of the signal that was in your data. And so there's a lot of really excellent and practical methods that have been developed in the context of homogeneous noise. Here's the kind of scree plot that we talked about. Yeah, there's just a bunch of approaches for this. And so today I'm going to focus though on a class of methods called parallel analysis. And so let me first give a little bit of an advertisement for it. Here are some snippets from a variety of surveys that all of which basically point to parallel analysis as a reliable and accurate method. Okay, and we'll see what it is in a moment, but you'll also see that it's really simple. Okay, so that makes it really nice and really interpretable. Right, so you got things all the way from, let's see, which one I want to point out to you. Things in the sciences to, here is also the kind of the classic elements of learning. There they talk about randomly scrambling each column. And so there's a really widely endorsed method with extensive empirical support. I was hoping I didn't get a chance. I forgot to take a picture of it before I left home. But But if you read Jeff and Raj's new textbook, they also talk about this technique. And so that's one more great course that endorses the method, I guess. Apologize. Okay. So what is it? The key idea here is to get sort of null distributions. I'm going to put that in quotes for the noise singular values by destroying the signal. Okay, so the idea is if I knew that noise floor, if I knew what the screen looked like, then I could pick everything that's above that screen. Okay. So how are we going to do that? Well, in this technique, in this so-called permutation-based parallel analysis, we randomly permute the entries in each column. So what does that look like? Here's a data matrix. And what I'm going to do is I flip through here, you're going to see that we go column by column, and every column you just shuffle the entries. Okay, so you do a random permutation of the columns. So as we go through, what I want you to observe is notice that on the left, you can kind of see that sort of plus-shaped structure of the low-rank signal. And as we kind of sweep to the right, you're going to see that structure kind of wipe away, right? So when you look at the permuted data on the right, you don't really see that low-rank structure visible anymore. Now, of course, it's not exactly what the SVD does, right? We're not looking at heat maps when we're doing the SVD, but there's sort of a nice visual way of illustration. Okay, so we randomly permute the entries in each column. That gives us the permuted matrix, compute the singular values, and then do this many times. So once we do this many times, now we can make for every singular value a little empirical histogram of what those singular values are for different random permutations. Okay. And what we're going to do, we're going to select the singular values of the data that rise above some percentile of the permuted data singular values. Another common choice is just to take the leading one, the first singular value of the noise, and then use that as a cutoff, going across like that. Okay. And so here, this correctly selects one component. Cool. So this is like a few lines of Julia code, right? It's relatively easy to implement, and it's really simple to interpret because the name comes partly from saying when you do those random permutations, you're sort of generating some parallel data sets to compare against that look noise-like. All right, so this is really simple, practical, and it turns out very effective. Right? There's all these surveys that have found it to be accurate. Oh, let's see. Not in these slides, but I kept it to be rank 1 just to keep the illustration simple, but you would see a second one pop up here. So maybe it would look like this. Yeah, great question. Okay. So here's where actually there's a subtle thing though, where if you had something that was like here, right, then if you chose that first one as a cutoff, you would say 1. And if you used like all of them, then you would choose 2. And so that so-called upper edge comparison tends to be more conservative. Great question. Okay, so what happens now when we have heterogeneous noise, right? This is part of the game we're playing today is let's take an existing method that works very well when there's homogeneous noise. Let's make the noise heterogeneous and see what happens. Here's that data, which is signal plus noise. After permutations, here's what we get for the permuted data singular values. And now we have incorrectly selected 9 components, okay? So what we found actually is that this permutation-based parallel analysis can really dramatically degrade when the noise is heterogeneous. Okay. And so now one thing we could do is we could just throw the method out and say, okay, we need to come up with something entirely new. But instead, what we're going to do is we're going to dig in and try to analyze what went wrong, right? And by understanding what went wrong, that's going to give us an idea to try to for how to fix it. Okay, so what went wrong in this case is that if you look at noise, so here I've made noise, which has a very simple form of heterogeneity. The top half is less noisy than the bottom half. Okay? But now when you do random permutation of every column, here's what that noise looks like after those random permutations. Okay? And you might notice actually it looks a lot like noise where what I've done is sort of averaged out the variances. So I've looked at like maybe noise of variance that's equal to the average of those two. All right. You can think of it this way. You've taken that energy, you've smeared it across the entire column. All right. So we just smeared it all across the entire column. That's what the permuted noise looks like. And now on the right, what I'm showing are actually the singular values that come out from those three matrices. All right. So in blue there is the original noise. Okay, so that's what the actual singular values of the noise look like. But after doing permutation, it looks like this green distribution. And indeed, that green distribution of singular values looks just like this yellow distribution of singular values, which come from this noise, which is generated, which is a homogeneous variance profile. Yes, question. Good question. Go column by column and then shuffle the entries in the column.
Oh, so shuffle.
Yeah, so up and down, but a separate shuffling for every column.
Is that a color figure? Or is that my eyes playing trick on me? Like, is this grayscale noise?
Oh no, this is colored. Yeah, and I think it's colored where red is positive and blue is negative.
Oh, I see.
Yeah, and then like white is roughly zero, I think. Yep. Yeah, sorry, I guess I switched up the heat map, the color map line.
Yeah.
So what we see here is that the permuted noise, though, is not representative of the original noise. So for example, if this was our data, there's no low rank signal here. This is just purely noise. And so the right answer here is to say 0. There's no, the rank should be 0 here, right? There's no components. But if we actually were to imagine doing permutation PA, what would we do? We would permute the noise, and then we'd maybe identify the upper edge of it, which is here. And then we would have selected however many singular values were above that. And you can see there's like, I don't know, maybe tens of them, right? That makes sense. So in essence, what's happened here is we've underestimated the noise floor. And as a consequence, we've over-selected, which is what happened in that previous example. Okay. And so here's sort of actually an informal theorem. We can say something more precise, which is actually we can say that the singular values of that permuted noise are going to asymptotically be the same as the singular values of the noise with a homogenized variance profile. Okay. Yes. Oh, yeah, sorry. These are histograms of the empirical singular value distribution. So this is like a frequency. That's correct. So to be a little more precise here, what we've done is taken the singular values of the noise. I forget the size of that matrix right now, but let's say there were 1,000 of them, singular values, and then we plotted a histogram of those 1,000 singular values. So this is from one instantiation of the matrix. Great question. Okay, there's some details actually improving this because the permuted noise no longer has independent entries. And so some of the standard results from random matrix theory don't immediately apply. So there's a little bit of work involved in proving this, but it does sort of what you might expect. So based on this, the insight we might have is, well, what we should do then is to do some kind of transformation that doesn't mess up the noise structure. And so that's going to be the idea. Here is to replace permutations with random sign flips of every entry, right? And since we're now moving things around, we're not going to mess around with the heterogeneity of the noise. And so here, everything else is the same, except all we've done here is we replaced random permutations with sign flips, right? I think this is one of the nice things where some insight into what went wrong can allow us to see like a surgical fix to make it work again. And so on the left here, you see the data. After sign flipping here, we have sign flip data. And you can see that even you can see like qualitatively that the statistics of the noise are preserved, right? You can see the same heterogeneity in the noise. So how does it work? Well, we saw it before when we have homogeneous noise and heterogeneous noise. Permutations go from working really well to dramatically over-selecting. But now when we have sign flipping, what we see is that we correctly now in both cases select one component. And notice the key here is that now the sign flip data correctly estimates the actual scree. Okay. Whereas over here, we are way underneath where it should have been. So sign flipping is really a simple and effective way to handle this heterogeneous example. And if you already have code for permutation-based parallel analysis, this is a one-line change. And actually, it's easier to implement, I think, than permutation-based parallel analysis. So I'll take a brief moment to talk a bit about some of the theoretical insights, what makes this work. And And today I'm going to focus more on just giving some of the high-level insights and ideas. I know we're getting near the end here, and also we're near the end of the day, maybe. And so I'll point you to the paper for more detailed statements. But here's going to be the idea is that when we start with data with homogeneous noise, if we look at data as signal plus noise, after sign flipping, what happened? Well, the sign flip signal looks kind of like noise now. The sign flip noise, well, that looks just like the noise, which makes sense because the noise here, in this case, is symmetric. And so if we sign flip, you have exactly the same kind of, you just get like another instance of noise. Okay, and so when you add them up, oh, I'm sorry. Okay. When you add them up, the sign flip data here looks a lot like the noise here. Okay. This is sort of the key insight. So sign flipping here destroyed the low rank signal structure, but it preserved the homogeneous noise. Likewise, now if we look at heterogeneous noise, right? Sign flipping, well, the noise and the sign flip noise look basically the same. What happened to the signal? It also looks scrambled up. It looks kind of like noise. All right, and so when you add them up, you get something here that looks a lot like the noise. Okay. Yes. Yes. Yeah. So I don't know how I'd plot that. Well, yeah. So, yes. And so here now, if we look at the singular values, here's the singular values of the data, the signal. Here the signal is rank 1, so there's only one non-zero. And then here's the noise. Okay. So on the left, we're going to look at homogeneous. On the right, heterogeneous. So now what I'm doing as I flip slides here is I'm making the data matrix larger. Okay, so the way you're going to see that is that the entries, the pixels there are going to get smaller and smaller. Okay, so as I kind of go to larger and larger. Oh, wait, no, maybe I haven't done that yet. Sorry. Oh, I'm sorry. Here we're just showing first the operation of sign flipping. Okay, so we saw this before. Here's what the sign flip data singular values look like. Here's what the singular values of just the sign flip signal looks like. It looks noise-like. There's a bit of a scree. As expected, the sign flip noise singular values look just the same. And now as I make that matrix bigger and bigger, you see those pixels getting smaller and smaller. And what you might observe is that these signal singular values after sign flipping, they're actually going down a little bit. They're getting smaller and smaller. Slowly, but they're getting smaller. Okay. So what's sort of the conclusion? So how do we put all these observations together to actually try to prove something rigorous about this? Well, the idea here is that the signal, if we look at the operator norm of it, sort of the maximum energy of it, that after flipping is much smaller, right? We've gone from something highly structured, right? You can think of the operator norm as some kind of proxy for how structured is this thing, down to something that's much smaller here. Because why? Because what we've done is we've smeared that energy across all of the singular, across the whole space, maybe I'll say it that way. Moreover, the flip noise is equal in distribution to the noise. So if we put these two facts together, what can we say? Well, the singular value of the flip data, well, if I plug in the flip data, that's just the flip signal plus the flip noise. And now here, if the operator norm of the flip signal is small, then if you know Weyls inequality, that will allow you to say that this is going to be similar to the singular value of the flip noise. But now, since the flip noise and the noise are the same in distribution, these two are going to have the same distribution. Okay, so this is sort of the heart of what's going on here. And so, in other words, the sign flip singular values on the left estimate the noise singular values all the way on the right in distribution. Okay, and so sort of the informal theorem we're able to prove here is that flip PA correctly selects the rank with probability 1. As long as the signal is, I'm going to leave in quotes here, delocalized. The idea is that you shouldn't have too much energy in just one part of the matrix. This is actually non-trivial to prove as well. We use a variety of recent breakthroughs in random matrix theory for analyzing these sorts of non-homogeneous random matrices. And there's lots of like matrix derivations after that to put it all together. Okay, so to summarize this part, we saw permutation-based parallel analysis. We saw how that works for homogeneous noise. I only showed you one example, but you could believe that it'll work very well in lots of scenarios. We saw how to extend that, or what happens when you have heterogeneous noise, and how using sign flips instead can sort of fix the problem that permutations had. We saw some theoretical insights into sort of why it actually works. And I'll point you to the paper for the theoretical guarantees, and we've got lots of simulations and things like that. We've also looked at cases where, for example, you have blocks of the matrix that have correlation. So in that case, you can sign flip each block at a time. And so the nice thing about these parallel analysis techniques is that they're very flexible, right? If you can think of a way to scramble the data so that it doesn't mess up the noise, then you have potentially a parallel analysis method. Okay, so maybe I'll conclude here just to say that heterogeneous big data is really everywhere, and I hope you got to see that it really poses a lot of really interesting and exciting challenges to be tackled. And so there's tons of work to do, and so there's an invitation to join us. And with that, thank you so much for your time.
Thank you very much, David. We have time for questions. Maybe while you're thinking of questions, I'll just mention that the first time I taught Boost 521 in 2017, David was in GSI class. I think the year after that, he won an outstanding GSI award. And I hope you got a small taste of why he might have gotten that award from today's presentation.
Thank you.
Yeah, I was wondering, your talk, the heterogeneity of the noise distribution comes with two different variances. How did they change like smoothly?
Sorry, in which part? Part 2 or part 3?
Both were either.
Yeah. So you're wondering if, so let me make sure I understood the question correctly. You're saying, what if rather than having like 2 or 3 or some finite number of noise variances, for example, it varied smoothly through the data, something like that?
Yeah.
Okay. Yeah. So in this second part, we did not need to assume we did not assume that there's only finitely many, I'll say, noise variances. The key assumption in the part 3, in the rank estimation for that work, the key assumption is that the noise has a well-defined asymptotic floor. There's like a well-defined asymptotic noise floor. So sort of in random matrix theory speak, it would be that the operator norm of the noise matrix converges to some number, has some limit. So as long as that holds, everything goes through. Now, you might then ask, does that, can that happen under this kind of scenarios you described? And the answer, my memory right now is yes. Yeah. So I think people have studied that scenario where you have smoothly varying. There's a variety of conditions people have studied there. For the first, for the optimally weighted PCA, a subtle thing is in that proof technique, it relies kind of crucially, that proof strategy relies crucially on the fact that there's a finite number of weights, a fixed number of weights. And so it's non-trivial how you would generalize that proof. Conjecture is that the same weights remain optimal, even when every sample can have its own noise variance. There's probably some kind of regularity required, I would guess. And the second thing I can say there is that notice that the smoothness actually doesn't matter there, because what we're doing is we're forming a weighted sample covariance matrix, right? So in that sum, it doesn't matter what order they're in, right? So so smoothness I think wouldn't help, yeah. But I think there would need to be some kind of regularity, maybe the off the top of my head, I would imagine, for example, that the variances maybe should be bounded, right? Like no more than something. Yeah, great question. But that's an open problem, so if you want to solve it, let me know.
Fantastic talk.
Thanks.
I have a question about science. I mean, I know that in the paper you have to present in a certain way, but I'm just curious. Did you stumble upon the idea of flipping,
Yeah, you want to know the
this works very well, and then you looked at theory and tried to show why this is good, or did you look at theory first and then this is a result out of that? I'm curious.
How the sausage got made. Okay, so here's the story. So I went to do a postdoc at Penn. My host there, Edgar Dobribon, had worked on analyzing permutation-based parallel analysis through this kind of a signal plus noise framework, and was able to prove some properties of permutation-based parallel analysis. He had a PhD student who was looking at that paper. I looked at the paper a little bit as well. We were thinking, is there some kind of extension we could do? And my rough memory is like this, that we were sitting in a room somewhere with a laptop and we said, let's try sign flipping. And then, seems to work. And then is this useful? And then for me, I was actually really amazed, delighted to discover, oh, wait, this would be really useful when we have heterogeneity because it doesn't mess up the structure of the heterogeneity. So it was kind of, at least by my memory, relatively happy accident that it kind of all fit within like sort of so close to things I was already thinking about. But yeah, I wouldn't say it was like, we carefully orchestrated things. Yeah, no, yeah. So yeah, thanks for asking. Great question. Yeah.
So for the same problem, if you have complex data, have you tried random faces instead of like
Yeah, actually, okay, so I have a collaboration with someone doing so-called ultra-fast ultrasound, and we've been looking at trying to do rank estimation for one of their problems, and we tried, yeah, but their data, I don't know, it doesn't, it's got a lot of other complexities, but we tried, and short story is, okay, tried it in one real data case. I mean, I guess we spent all of 20 minutes on it. This is like as of 2 weeks ago, we tried it. And it worked okay there. But I think if you actually have data that fits the model, I would say. So I think that data doesn't fit the model well enough. If you have data that really fits the model, then yeah, I think that would work very well. And so generally, actually, we made some attempts. I made some attempts at trying to prove. It feels like there ought to be a theorem that roughly says if you scramble with more operations, you get more signal destruction and you do better. And by the way, actually, this is something that is worth pointing out if you want to try parallel analysis methods in your work, is one of the major weaknesses of parallel analysis methods is if you aren't sufficiently able to suppress the signal, what you end up with is something that looks like a noise floor, but it's inflated. So it's sort of like the energy of the signal is still there. So if you have like a really strong signal component, what you end up with is you sort of end up with an inflated noise floor. Which means that you might underselect, because you might say, you might think the noise floor is here, it's really here, and so there's something kind of in between there that ought to have been selected. So this may be a long-winded way of saying that, yes, I think it should work very well. The theory, I think, would be not too hard to do, and there are some potential benefits. Yeah.
Let me just follow up on that, because I think the question was, do you just do an ordinary sign flip or do you do a random phase? And I would guess it might depend on the distribution of phase that you start with. If you
Oh,
start out
yeah.
with complex noises isotropic, probably either way would work. But maybe if it's anisotropic,
That's a good point.
which we don't really have in the noise and MRI, which I work on, right? But it's
Yeah.
ultrasound, I don't know, right?
That's a good point. I hadn't thought of that. Yeah.
But it's what you're.
Yeah, I totally agree. That's really, that's really
I
important.
have a question. So the dependence on the signal is a little bit unappealing in a way. So if we said our problem was to maximize the sum over I of the recovery, the R sub i's, instead of just one component at a time. So aggregate them somehow so we get some, maybe compromised weights that works well. Is that totally intractable? Have you thought about it? Did
Yeah,
I see this 5 years ago?
Yes. Yes. So there's that's right. There is a version of our paper, I think, where we had some kind of comment about this, at least a remark. I don't know if the final version still has a remark about that, but yeah, I think what we found was, so at least I don't know of a simple solution for those weights. And then secondly, I think I played around at one point doing like numerical optimization of it. And I didn't try very hard, but just a little bit I tried, it was like a little bit non-obvious how well it didn't seem to be working that well. And I suspect it's because of this like, it doesn't like, there's this invariance to the scaling. And so that would have to be accounted for, I think, properly.
Oh,
Yeah.
right.
Yeah.
Let's thank David one more time. Sorry, now.
Oh, okay.
Yeah, they're waiting.
Oh, we better.
Oh, that's very nice of them. Yeah.